Welcome to the Padhai Kar Lo JEE Preparation channel. You can practice more problems on this exact topic on our Padhai Kar Lo Android app, link in the description below, or on our website padhaikarlo.com. Today's topic is Hooke's law, the foundational proportionality between stress and strain that underlies every elasticity numerical. Let's begin. Hooke's law states that within a material's elastic limit, stress is genuinely directly proportional to strain. Stress equals the modulus of elasticity times strain, where the modulus of elasticity is a fixed constant characterizing a specific material's own inherent stiffness. This linear proportionality holds only up to the elastic limit. Beyond that specific point, the material enters a plastic region where stress and strain no longer relate linearly, and any deformation genuinely becomes permanent, irreversible, even after the applied stress is completely removed. For a simple spring, Hooke's law is more commonly written directly in terms of force and extension, F equals minus kx, where k is the spring constant, and the negative sign indicates the restoring force always points opposite to the direction of displacement. This specific form is exactly what produces simple harmonic motion, when a mass attached to a spring is genuinely displaced and then released. When two springs are connected in series, they experience the exact same applied force, but their individual extensions add together. This gives a combined effective spring constant found from the reciprocal formula. 1 over k equivalent equals 1 over k1 plus 1 over k2, meaning the combined series spring constant is always genuinely smaller than either individual spring constant alone. The combination becomes softer, easier to stretch. When two springs are connected in parallel, they share the exact same extension, but their individual restoring forces add together, giving a combined effective spring constant that's simply the direct sum. K equivalent equals K1 plus K2, meaning the combined parallel spring constant is always genuinely larger. The combination becomes stiffer, harder to stretch. This exact same mathematical pattern, reciprocals add for series, direct sum for parallel mirrors, resistor combinations in circuits, and recognizing this direct parallel makes remembering both rules considerably easier. For any G Hooke's law numerical, first correctly identify whether the problem is genuinely describing a spring system using F equals kx directly, or a solid rod or wire being stretched using stress equals modulus times strain instead. These are the exact same relationship, just expressed using different specific variables suited to each particular physical situation. For spring combination problems, correctly identify whether the springs genuinely share the same force series or the same extension parallel before choosing the appropriate combination formula, and remember energy stored in a stretched spring is 1/2 kx squared, the formula that appears constantly in combined mechanics and elasticity numericals. A frequently tested trap, cutting a single spring into two genuinely equal halves doubles each individual half's own spring constant, since a shorter spring or the exact same material is proportionally stiffer. This specific inverse relationship between spring length and spring constant is commonly overlooked. Let's recap. Hooke's law states stress is proportional to strain within the elastic limit, and for springs specifically this becomes F equals minus kx, the restoring force behind simple harmonic motion. Springs in series add reciprocally, becoming softer overall, while springs in parallel add directly, becoming stiffer overall, mirroring resistor combination rules exactly. And remember, cutting a spring in half doubles its spring constant, a frequently tested, easily overlooked trap. That's Hooke's law. Keep the series versus parallel spring combination rules and the cut spring trap sharp. They're consistently tested together. If this video helped, please like it and subscribe to Padhai Kar Lo for more JEE preparation content just like this. See you in the next one.